Hello, my name is Ryan Chazen. I'm a student in Math 24, Discussion 21D, and I'm taking this class in fall 2020. Today I will be presenting my video project on the Verhulst model. So what is the Verhulst model? In order to understand the Verhulst model, we first have to understand the Malthus model, and that is given by the equation dy dt equals ry, and this is an exponential growth. So in order to see this, I have a graph on the right side where the blue is the population and the red line is the amount of resources. And so we have a point of crisis here. So when the population exceeds the resources, the population will actually decline, but the Malthus model does not represent this. So the Verhulst model does represent this. And as you can see here on the graph, this is the Verhulst model graph. And it's the number of individuals and the time. And you can see that the growth rate increases fast until it nears the carrying capacity, and then the growth rate decreases significantly until it reaches the carrying capacity. And the maximum growth rate is 0.5 L. It happens right here in the middle. And this is important to know for the example on the next slide. And the Verhulst model is given by the equation dy dt equals r, which is initial growth rate, 1 minus y over L, carrying capacity, times y. And this is also a form of logistic growth. The Verhulst model is a first-order, nonlinear, separable differential equation. So here's an example of the Verhulst model. So first I gave the Verhulst equation up the top there for reference. And the question is, suppose a population of butterflies is growing according to the logistic equation. If the carrying capacity is 500 butterflies and R equals 0.1 individuals over individuals times month, what is the maximum possible growth rate for the population? So we have L equals 500 because there are 500 butterflies. We have R equals 0.1 because that is the growth rate. And we have y equals 500 over 2, which equals 250. And remember on the last slide, I showed that this was because the maximum growth rate is 0.5 L. And when we plug that into the equation, we get dy dt equals 0.1 times 1 minus 250 over 500 times 250. And that gets us dy dt equals 12.5 individuals per month. And that is the maximum possible growth rate for this population. Thank you for listening to my presentation. I really enjoyed this semester. Here are my references. Thank you so much. Have a great day.